In this video, I'm going to cover chapter 10 of my stochastic modeling book about continuous time Markov chain. This video in particular is also related to two other chapters, chapter 7 about discrete time Markov chain and chapter 9 about Poisson processes and the exponential distribution that are also covered in this playlist. This picture shows you more precisely the different topics and results we are going to cover and how those different topics are related. As for the previous video in this playlist, the video description also gives you the table of content with the different topics we are going to cover and the specific timings. Just click on the timing to go directly to the topic you are interested in. And at the end of the video description, you will also find a link to the presentation I wrote for this video. Just click on the link if you want to download the PDF file. So the concept of Markov chain in general was introduced by Andrei Markov. I also have a picture of Andrei Kolmogorov here who prove some of the early results in the field of continuous time Markov chain. So the main objective in this field is the same as in discrete time. The goal is to understand the limiting behavior of the process, looking at those quantities here, fty, pt, xy, that again appear here. That's the fraction of time spent in a state y in the long run, and the probability that the process is in state y at some large time, given that it starts from state x. Those quantities are also related to the notion of mean recurrence time, which is a third important question about continuous time Markov chain. The mean recurrence time is the expected amount of time you need to return to a state when starting from this state. And exactly like for discrete time Markov chain, the key ingredients to be able to answer those questions and compute those limits are irreducibility, transience, null recurrence, and positive recurrence. Another important concept also is the stationary distribution that will describe the limiting behavior here in the case of positive recurrence. In the case of transience and null recurrence, everything goes to zero. But in the case of positive recurrence, we have convergence to the stationary distribution. Notice that in this slide, the notion of aperiodicity does not appear. That was an important concept in the framework of discrete time Markov chain. We needed aperiodicity to ensure convergence of those limiting probabilities here. That was Pnxy in the case of discrete time Markov chain. In the context of continuous time Markov chain, the notion of period or aperiodicity is not defined because things evolve in continuous time, and in fact, the notion of aperiodicity is not needed to have convergence of those limiting probabilities. All right, so first, I'm going to define what we mean by a continuous time Markov chain. The definition is pretty much the same as in discrete time. It says that given the present, past, and future are independent, or we can formulate that also by saying that given the past, including the present, to predict the future, you can forget about the past and only remember the present. That's some kind of memoryless property of the process. That's what we call the Markov property. So the definition is more or less the same as in discrete time, but now, because things evolve in continuous time, instead of being described by transition probabilities, the process is going to be described instead by what we call transition rates. The word rate has to be understood the same way as the rate of a Poisson process. And using those transition rates, you can construct a matrix that we call the intensity matrix. So have in mind that transition rates can be viewed as the analog of transition probabilities in discrete time, and the intensity matrix can be viewed as the analog of the transition matrix in discrete time. Then, the first main result we are going to prove shows that any continuous time Markov chain can be written as the combination of a discrete time Markov chain called the embedded Markov chain that describes the sequence of states visited by the process, and a collection of Poisson processes or independent Poisson processes or independent exponential random variable that are going to describe the time of the jumps. So discrete time Markov chain, chapter 7, answers the question, where do we jump next? And Poisson processes, chapter 9, will answer the question, when do we jump next? Okay, so where and when. And combining those two aspects will have an explicit construction of the continuous time Markov chain a priori at all times. Except in one particular case, it's when we have to deal with a continuous time Markov chain with explosion. So we call continuous time Markov chain with explosion a process that is going to jump infinitely many times, and so escape to infinity in some sense in a finite amount of time, called the time to explosion. And in this case, obviously, the first result here that we are going to prove is only going to give us an explicit expression of the process until the time to explosion. After that time, the process is no longer defined. So third, I'm going to briefly explain what we mean by continuous time Markov chain with explosion and give you an example of such a process. Then, starting from that, we'll be able to start answering those questions by going through the main ingredients. So starting with the notion of irreducibility, related to the notion of communication classes, recurrence, transience, the distinction between null recurrence, positive recurrence. Again, remember, notion of period is not defined for continuous time Markov chain. That was an important ingredient for discrete time Markov chain. This notion now disappears, but those ones are still important. So after defining all those notions, we'll see that's a very easy result, that in fact, the continuous time Markov chain and its embedded Markov chain have in fact the same communication classes. In particular, if the embedded Markov chain is irreducible, then the continuous time Markov chain is going to be also irreducible. Those two processes also share the same transient and recurrent states. Okay, any state that is recurrent for this process is recurrent for that one, and same for transients. However, we'll see at the end of this video that there exists continuous time Markov chain such that embedded Markov chain and continuous time Markov chain do not share the same null recurrent or positive recurrent state. I'm going to conclude the video with a counterexample. The fact that the continuous time Markov chain does not inherit the same property as the embedded Markov chain for null recurrence, positive recurrence, are due to some kind of distortion of time when you go from continuous time to the embedded Markov chain in discrete time. All right, so then next, the goal is to understand the stationary distribution of the process, if there is one. Then to understand this stationary distribution, the next step is going to be to study what we call the backward and forward Kolmogorov equations. So those equations are ordinary differential equations for those quantities, Ptxy, probability of going from state X to state Y in t units of time. So these are ODEs for those quantities that also involve the transition rate or the intensity matrix. All right, so once we have those equations, we'll be able to study the stationary distribution. So next, I'm going to define the notion of stationary distribution. The definition is more or less the same as in discrete time. And using those backward and forward Kolmogorov's equation, we'll be able to prove that a distribution pi on the state space is stationary if and only if pi q equals 0, where q is the intensity matrix. So think of this linear equation, pi q equals 0, as some kind of analog of pi p equals pi in discrete time, where p is the transition matrix. So that's the main tool, the main ingredient to be able to find the stationary distributions of the process, if there are some. And using this result, we'll also be able to prove that any reversible distribution is stationary. That's another trick to find the stationary distributions. Then with all that, we'll be able to give a complete picture of the convergence theory for continuous time Markov chain, and exactly like for discrete time, excluding again this notion of periodicity, we'll be able to prove that if a continuous time Markov chain is irreducible, then either all states are transient or all states are recurrent. That can only happen when the state space is infinite, in which case those quantities, fraction of time spent in a state and probability of finding the process in a given state in the long run, are all going to converge to zero. Or, other possibility, all the states are positive recurrent. In this case, there exists a unique stationary distribution. Uniqueness is like follows from irreducibility, while existence follows from positive recurrence. And in this case, the fraction of time spent in a state or the limiting probabilities here are going to converge to a positive limit described by this unique stationary distribution. Using those quantities, we can also have an explicit expression of the mean recurrence time. So this will cover all the convergence theory for continuous time Markov chain. Now, to conclude this video, I'm going to use this result, and in particular the fact that positive recurrence, not only in the case of continuous time Markov chain, but also in the case of discrete time Markov chain, is equivalent to the existence of a stationary distribution, to prove that there exist continuous time Markov chains that are positive recurrent, but such that the corresponding embedded Markov chain is null recurrent. So this will tell us, to conclude, that the continuous time Markov chain and the embedded Markov chain indeed have the same communication classes, transient state and recurrent state, but they might not have the same null recurrent or positive recurrent states. First, let's define properly the notion of continuous time Markov chain and also transition rates and intensity matrix. So I start with a process xt, that's a continuous time process. Xt is a short to mean the collection of all the random variables xt for t larger or equal to 0 real number. T is continuous time, that's a real number now. And we said that this process is a continuous time Markov chain with state space S finite or countable if those two conditional probabilities are equal. So let's look first at this event that appears here again. That's a typical event in the future. In this expression, think of time t as the present time, and S is a very general time in the future. B is a very general subset of S, of the state space S. Notice that because S is finite or countable, B is always going to be a Borel subset of S. And so, because S is a general time in the future and B is a general subset of S, XS in B is a typical event, a very general event in the future. This equation tells you that the probability of this event given Ft is the same as given Xt. Ft is the sigma algebra generated by the process from time 0 to time t. That's your knowledge of the process from time 0 to time t. That's your knowledge of the past, including the present, while Xt is your knowledge of only the present. So what this equation says is that the probability of a typical event in the future, given past and present, is equal to the probability of the same event, but given only the present. And so to predict the future, if you know past and present, you can forget the past and only remember the present. That's exactly the same as the Markov property in discrete time. Another way to formulate this property would be to say that given the present, past and future are independent. Now, notice that when I covered discrete time Markov chain in chapter 7, we chose for the present time n and for the future time n plus 1. n plus 1 is called the successor of n on the set of natural number. That's the smallest integer that is strictly larger than n. On the set of real number, this notion of successor does not exist. If t is a real number, there is no smallest real number that is strictly larger than t. So that means that there is no next time step. And because of this reason, it seems that to fully define the process, the continuous time Markov chain, we need to have a knowledge of the full collection of all the transition probabilities. Ptxy, that's the probability of going from state x to state y in t units of time. It seems that we need to know those transition probabilities for all t to fully understand the process. There is no one-time step transition probabilities like in discrete time from which we can define the full collection of transition probabilities. However, because of this Markov property that tells you that you can forget the past, it seems that if we know p epsilon, let's say p epsilon xy for all epsilon small, then we can construct the process, we can understand the process from time 0 to time epsilon, then forget the past, and then reapply this p epsilon xy to understand the process up to time 2 epsilon, and continue like that to understand up to time 3 epsilon, 4 epsilon, and so on. So it seems that if we know not this full collection, but only p epsilon xy for all epsilon small, then we should be able to reconstruct this full collection of transition probabilities. And indeed, this is the case in the following sense. It turns out that this collection of transition probabilities, Ptxy, are solution of some ordinary differential equations. That's what I called just before the backward and forward Kolmogorov equation that involve what we call the transition rates of the process. So let's define this notion. The word rate here has to be understood in the same way as in the context of Poisson processes. So let's take two states x and y that are different, and let's look first at this quantity. P epsilon xy is the probability of going from x to y after epsilon unit of time. So you start in state x, and we look at the probability of being in state y, another state, after a very short time interval of length epsilon. Then we divide this by epsilon, and we take the limit when epsilon goes to 0. I'm going to call this limit Cxy. Let's assume that this limit exists. I'm going to call it Cxy. So to see that indeed this definition matches the notion of rate defined in the previous video, chapter 9, Poisson processes, remember that when I define a Poisson process, or more generally a Poisson point process, we could think of the process as a limit of a sequence of Bernoulli processes. And in this definition, we said that something happens at rate mu if the probability that it happens in a very short time interval of length epsilon is of the order of mu times epsilon. And that's exactly what this definition says. The fact that this limit exists and is equal to Cxy means also that if you multiply by epsilon on both sides and take epsilon small, means that the probability of a jump from x to y in a very short time interval of length epsilon is of the order of Cxy times epsilon. So that fits the definition of rate in the previous video. We can indeed call this limit the rate at which we jump from x to y. Cxy is exactly interpreted as the number such that the probability of a jump from x to y in a very short time interval of length epsilon is of the order of Cxy times epsilon. All right, so we are going to assume that this limit exists and is finite. And in fact, we are going to assume more than that. we are going to assume more generally that the rate at which the process jumps not from x to y only, but from x to any possible overstate is finite. That's just to avoid having instantaneous jump in the process. Okay, and so that brings us to the next definition. We are going to say that the continuous time Markov chain xt is conservative. That's going to be our assumption during this video if we have no instantaneous jumps. And the way you formulate that mathematically is by saying that this limit here exists and is finite. So let's look carefully at this term. You see that p epsilon xx is similar to the p epsilon xy. P epsilon xx is the probability starting from x that you are still in state x after a very short time interval of length epsilon. 1 minus this is the probability that you jump from state x to another state, any other state, in a very short time interval. Again, we divide by epsilon, take the limit when epsilon goes to 0, exactly like before. This is interpreted as the rate at which we jump from state x to any other state. We are going to assume that this limit is finite, okay? That just to impose for the process no instantaneous jump. And so each time the process visits a state, it's going to stay there a little bit, at least a very short time, before it can jump again. You do not have infinitely many jumps in a very, very short time interval. So that's the assumption. Notice that this limit here is also equal to the sum of the cxz, where cxz is the rate at which we jump from x to z. The way you see this is just by noticing that this is the probability that you jump from state x to any other state, the 1 minus. So that's exactly the sum over z different from x of p epsilon xz. But if you divide everybody by epsilon and take the limit, then you indeed end up with the sum of the cxz for all z different from x. Okay, so that's our assumption. We assume that the continuous time Markov chain is conservative. We do not have instantaneous jumps. Strictly speaking, for a very general continuous time Markov chain, we may have instantaneous jump, but it turns out that those type of processes are not very realistic or useful in practice. That's the note I added here. Continuous time Markov chain used in practice are conservative. So that's a mind assumption to assume that this limit here is finite. Then, assuming that the system is conservative, so not only those cxy are finite, but also the infinite sum for z different from x of the cxz is finite. Having this assumption, we can define the notion of intensity matrix that's going to play an important role after to study the process. So the intensity matrix is going to be the matrix Q, capital Q. I'm going to call the coefficient of this matrix QXY, where x and y are two possible states. That's going to be more or less the matrix of the transition rates. Exactly like the transition matrix in discrete time was the matrix of the transition probabilities. So more precisely, QXY is going to be equal to CXY if x is different from y. Notice that in this definition here, if we impose no instantaneous jump, indeed, for x different from y, CXY exists and is finite. But if x equals y, then eventually you have that p epsilon xx, when epsilon is small, is going to be close to 1 divided by epsilon. This goes to infinity. So this CXY is finite, is well defined and finite only for x different from y. So that's what we use for the coefficient QXY of diagonal when x is different from y, but to define the matrix on the diagonal, we are going to say that Qxx in general is equal to minus this sum here, minus the sum for z different from x of the Cxz. And so the interpretation of the terms in the matrix are that if x is different from y, Qxy is the rate at which we jump from x to y, but if x equals y, Qxy or Qxx is going to be minus the rate at which we jump from state x. Alright, so now notice that in view of the expression of the coefficient here, if you look at the sum of all the coefficients on the same row, you obtain 0. Okay, the coefficients on the same row add up to 0. Remember that in the case of discrete time Markov chain, the analog of the intensity matrix was the transition matrix. That was the stochastic matrix, in which the sum of the coefficients on the same row was equal to 1. That's what we call a stochastic matrix, meaning the flow out of a state is equal to 1. In this case, the interpretation of is different. Instead, we look at weights. Those Cxy might be larger than 1. We do not have a stochastic matrix anymore, but the sum of the coefficients on the same row is equal to 0. Now let's prove that any continuous time Markov chain that is a conservative system can be viewed as the combination of a discrete time Markov chain describing the sequence of states visited by the continuous time process, and also a collection of independent Poisson processes describing the times between consecutive jumps of the process. So, more precisely, we are going to look at a continuous time Markov chain xt. We assume that the process, again, is conservative. The jump from any state is finite. And for this process, we are going to assume that Qxx is different from 0. The case Qxx equals 0 is trivial. I remind you from the definition of the intensity matrix that Qxx is minus the rate at which we jump from state x. Qxx equals 0 would mean that once you are in state x, because the jump at which you jump from that state is 0, then you stay there forever. In this case, the Markov chain at state x would get stuck and would not move anymore. Instead, we assume that Qxx is different from 0, so meaning from the definition of the intensity matrix that Qxx is strictly less than 0. This means that the process, when in state x, is going to jump to another state at a positive rate. But still the rate is finite. Then I'm going to also introduce this time t. So, like in the previous slide, think of little t as the present time, and capital T is the smallest s larger than t, such that xs is different from xt. That's exactly the time to the next jump. That's the time of the first jump after, strictly after time t, so time to the next jump. And the theorem we want to prove says the following. It says that, so we look first at capital T minus little t. Capital T is time to the next jump, so capital T minus little t is going to be the time we have to wait until the next jump. So the theorem says that the probability that capital T minus little t is larger than u, given that at time t the process is in state x, is going to be exponential, is going to be equal to exponential u times Qxx. Remember, have in mind, Qxx is negative, so uQxx is negative, and this exponential is indeed between 0 and 1. That's a probability. Okay, so what this tells us is that the time we have to wait until the next jump is exponentially distributed with parameter minus Qxx. All right, so that's the first result. And the second part of the theorem says that at this time t, time to the next jump, the probability that the process is in state y, again, given that we are currently in state x, is going to be equal to minus qxy over qxx. Remember, qxy is the rate at which we jump from x to y, and minus qxx, the rate at which we jump from state x. So the probability that the jump is from x to y is equal to the rate at which we go from x to y divided by the rate at which we jump from state x to any possible other states. Right, so this theorem answers two important questions: when and where. When is the next jump, and where do we jump next? And this tells us more or less that each time the process is going to visit state x, it's going to jump after an exponential amount of time with rate minus qxx, and it tells us also where do we jump. We jump to y with this probability. It's true for all y different from x. And you see also the connection with Poisson processes, or exponential random variable on this side, that tells you when we jump. And here we have implicitly some kind of discrete time Markov chain that we call the embedded Markov chain with those transition probabilities. So more precisely, you can understand the result as follows. The first part tells you that the waiting time in state x, each time you visit state x, you are going to jump from that state after an exponential amount of time with rate minus qxx. That's this sum, that's the rate at which you jump from x to any other possible states. And this part tells you that the sequence of states visited, now if you ignore the actual time of the jump and you just look at the sequence of states visited, then this sequence of states is described by a discrete time Markov chain that we call the embedded Markov chain. I'm going to call this process yn to differentiate from x. And this Markov chain has transition probabilities given by this that you can write also as p bar xy, probability of going from x to y, is equal to cxy, rate at which we jump from x to y, divided by the sum, that's the rate at which we jump from state x to any other possible state. Notice also that I'm using the notation p bar here to differentiate like the notation we use for the transition probabilities of this discrete time Markov chain and the other p that we used before that are the transition probabilities, but for the continuous time Markov chain. Right, so before we prove this result, in fact, I want to comment a little bit on the intuition. It turns out that using the definition of a continuous time Markov chain and the Markov property, we can in fact guess that this time indeed must be exponentially distributed. And also that the sequence of states visited should be described by a discrete time Markov chain. So why is that? So that's the next part of the slide. That's to explain the intuition behind this result. So the Markov property tells us that given the present, past and future are independent. You can apply that to the question when and to the question where. So if you apply this, if you think of the Markov property, what the Markov property says in terms of waiting time, it says that, again, given present, past, and future are independent. So this also means that the time to the next jump, which is in the future, and the time since the last jump, which is in the past, given the present, must be independent. But saying that time to the next jump and time since the last jump are independent means exactly that the waiting time between jumps must be memoryless. Okay? So the Markov property implies that the times between jumps must be memoryless, but we proved in the previous video that the only continuous random variable that is memoryless is exponential. So we can expect exponential directly from the Markov property. Time to the next jump in the future and time since the last jump in the past are independent. This means that the waiting times are memoryless and so they must be exponential. This argument does not tell us about the rate, but that tells us that this indeed must be exponential. The same reasoning can be used to the question not when, but where. Same story here, given the present, past, and future are independent. So given that at time t we are in state x, the previous state we visited and the next state we are going to visit must be independent. This tells us exactly that you can forget about the past in terms of states visited, and so indeed the sequence of state visited must be described by a process that is memoryless. That must be a discrete time Markov chain that gives us the second statement. Next state visited in the future and last state visited in the past are independent given the present, and so the sequence of state visited must be a discrete time Markov chain. So that's the intuition behind this result, but again, point number 2 here still doesn't tell us about those transition probabilities. But there is another way to interpret this result and have an explicit construction of the process in terms of collection of independent Poisson processes. And the idea is the following. So assume that at some time t the process is in state x, and the way you can construct the process based on those two properties is to say that, well, at that time where the process jumped to state x, start exponential clocks that I'm going to call tau z for all z different from x. So that means that each time you visit x, you start exponential clocks on each of the other states. The exponential clock attached to state z is going to be exponential with parameter cxz, which is the rate at which we jump from x to z. And then, to construct the process, just wait until one of those clocks rings, and when one clock rings, let's say it's the clock attached to the state y, then at this time you jump and you decide to go to state y, exactly like in the statement here. Okay? Then we can understand this result, like the two terms in blue, the rate of the exponential and the transition probabilities here of the embedded Markov chain, from the superposition property for Poisson processes. Or in this case, I'm going to use the superposition property for this collection of independent exponential random variable. We saw that the superposition property tells us that if we have a bunch of independent exponential random variable, the minimum of all of them must be exponential with parameter the sum. And the minimum of all of them is exactly going to be the time to the next jump. And so the time we have to wait until the next jump. And so from that we can deduce from superposition property, time until the next jump, which we call tau, is the minimum of all the tau z, and that's indeed exponential with parameter the sum of all the rates. Okay? But notice that the sum of all the rates here, okay, by definition, it's minus qxx. So that explains, that gives us a construction that is consistent with the first part of the theorem here. Then this answers again the question when. To answer the question where, just say that the probability that at the next jump we go to state y is exactly the probability that this random variable here, tau, first time at which one of those clock rings. So this is equal to the probability that tau is equal to tau y. But again, by the superposition property, the probability that tau is equal to tau y is equal to the rate of this exponential clock for z equals y, the rate of tau y is cxy divided by the sum of the rate of all the tau z. That's exactly the sum of all these rates. And you find again that here cxy divided by this sum is exactly qxy, it's this term, divided by minus qxx, that's this term here. So that gives you some kind of explicit construction of the process in terms of collection of, using a collection of independent Poisson processes. All right, so now how can we prove this result? So first, notice that because the process is time homogeneous and we have also the Markov property, it's enough to prove the result when little t equals 0. Instead of saying that the process is in state x at some time t and we look at what's going to happen next, we can just say, let's start directly the process at state x, and capital T, or capital T minus little t becomes capital T, and that's just the time of the first jump. It's enough to prove the result in this case. So to prove the result, the idea is to study another discrete time Markov chain in the background. That's not going to be the embedded Markov chain. The embedded Markov chain ignores the time of the jumps. Instead, we are going to look at a discrete time Markov chain that keeps track of the process xt in continuous time, but only at times that are multiples of epsilon. So, more precisely, I'm going to fix an epsilon positive, typically small. Eventually, I'm going to take the limit when epsilon goes to 0 to get the result. And we are going to define this process Zn epsilon. That's going to be equal, so n is an integer, but this process at time n is going to be equal to x n epsilon. So that's exactly the process that keeps track of the continuous time process at times multiples of epsilon only. That's called the epsilon skeleton of the continuous time Markov chain. And you see that here time t plays an important role. So the idea will be to basically prove that this result is in fact true for this discrete time Markov chain, and use the fact that in the limit when epsilon goes to 0, this process indeed described accurately the continuous time process. So the idea is kind of to prove the theorem for this new process, and for that I need to introduce some kind of analog of time t. That's going to be the time sigma sub epsilon. The sigma epsilon is the first time at which the epsilon skeleton is going to jump. And if you think of the definition, because this keeps track of the continuous time process at times that are multiple of epsilon, sigma epsilon is exactly the first time s that is a multiple of epsilon, so of the form epsilon times an integer, such that the value of the continuous time process at time s is different from the initial value of the process. And in this case, because little t is 0, we have x0 equals little x. All right, so we can explain that using a picture. So here, let's assume that you have a realization of your continuous time Markov chain, because we start from state x at time 0, we are in state x here, and then at some time, capital T, this time here, the process is going to jump to another state, let's call it y, exactly like here. So, this is the realization of the continuous time Markov chain. Now, you can visualize the epsilon skeleton from this picture by just looking at all the times that are multiple of epsilon. That's those times with a black dot here. Okay? So the epsilon skeleton at this time is at x, and then here it's still at x, but then at this time, sigma epsilon, it's going to go to state y, and then it's still at y, and so on. So the line here shows realization of the process in continuous time. The dots show the corresponding realization, but now for the epsilon skeleton. Now, if you look at the picture, you see that this process, this epsilon skeleton, so not at time sigma epsilon, 1 unit of time for the continuous time process corresponds to 1 over epsilon units of time for the epsilon skeleton. So at time sigma epsilon over epsilon, the epsilon skeleton is going to be at state y, exactly like xt. You see also that the only difference, like the difference between time capital T and time capital sigma epsilon is this length here, which is less than the length between sigma epsilon minus epsilon and sigma epsilon. So the time increment here is less than epsilon. So when epsilon goes to 0, what we expect is that sigma epsilon converges almost surely to T, and also this random variable is going to converge almost surely to xt. So indeed, the epsilon skeleton is a good approximation, at least when epsilon is small, of the continuous time process. So I'm going to write this result. That's something we are going to use, except that there might be a complication in the process here if things don't go very well. So what can happen is that the continuous time process jumps at time t to state y, but before the next multiple of epsilon is going to jump to another state, z, let's say, in which case the epsilon skeleton is going to miss the visit in between those two times. And in this case, this random variable is not at all equal to this one. That's one possible problem. Things can be even worse. It's if, for instance, the continuous time process jumps to state y, but before the next multiple of epsilon, which is time sigma epsilon, is going to jump back to state x, in which case the continuous time process jumped twice in between here, but the epsilon skeleton did not catch that. And in this case, not only the target site is not going to be accurate, but also the time of the first jump is not going to be accurate. The epsilon skeleton is going to overestimate the time to the next jump. Now, it turns out that, in fact, we still have this convergence almost surely, okay, when epsilon goes to 0, and this follows from the definition of weight and the fact that the system is conservative. The fact that the system is conservative means that the probability of a jump from state x in an interval of length epsilon should scale like epsilon, okay? Now, if we fix some time, let's say time s that is not infinite, like a fixed time, then the number of that corresponds for the epsilon skeleton to s over epsilon times steps, okay, units of time. And so in particular, in some finite amount of time in continuous time, the number of time steps for the epsilon skeleton scales like 1 over epsilon. But from the definition of weight, we know also that, and the fact that the system is conservative, we know that the probability of one jump in such an interval scales like epsilon, but the probability of more, strictly more than one jumps is going to be negligible compared to epsilon. That's what we call a little o of epsilon. And so that tells you that for any fixed time s, if epsilon is very, very small, okay, even if the number of time steps for the epsilon skeleton scales like 1 over epsilon, because the probability of multiple jumps in an interval of length epsilon is negligible compared to epsilon, the probability of having multiple jumps in the same small time interval before time s is going to be a little o of epsilon divided by epsilon. That goes to 0 when epsilon goes to 0. And so that shows that indeed we have those convergence, because when epsilon is very small, the probability of two jumps in this time interval goes to 0. So that's the first ingredient we need to prove this result. We have basically a connection between the continuous time process and the epsilon skeleton, in the sense that this time, first time at which the epsilon skeleton jumps, is going to be roughly capital T when epsilon is small, and the next state visited by the epsilon skeleton is the same as the next state that is going to be visited for the continuous time process. So we are going to use those two almost sure convergences. So then, next step, because the goal is to prove the analog, but now for the epsilon skeleton, we need to better understand this event and this event, but now for the new process in discrete time, and using basic properties of discrete time Markov chain and the Markov property, we can say that the probability that this time, sigma epsilon, is equal to epsilon n. Remember that must be a multiple of epsilon, so that's of the form epsilon n. And the probability that at this time the process is going to jump to state y is exactly the probability that n minus 1 time steps in a row, from the point of view of the discrete time Markov chain, this process is going to stay in state x, but because 1 unit of time for the epsilon skeleton is epsilon unit of time for the continuous time process, the transition probabilities for this process are p epsilon xy. So we want to stay in state x n minus 1 time steps using the Markov property, the fact that you can forget the past and so on. You can say that the probability that sigma epsilon is larger or equal to epsilon n is exactly p epsilon xx. We stay in state x, epsilon unit of time, and this n minus 1 times. So by Markov property, you forget the past, so you just have a product of probabilities. So that's p epsilon xx at the power n minus 1. But at exactly this time, you don't want to stay in state x, you want to jump to state y. That's this event, and for that, you need to go from x to y in this time interval of length epsilon. The probability is exactly p epsilon xy. Okay, so you see that here we have a probability that tells us something about the distribution of sigma epsilon and also about the distribution of the next state visited. So the last ingredient we need, the third one we need to be able to prove the result, is a way to write the transition rates of the process that are going to appear here when we take the limit when epsilon goes to 0, and the coefficient qxy and qxx of the matrix. The result is stated using the coefficient of the intensity matrix, not the transition rate. So we need to connect the two, and the way we connect the two is just like that. By definition of the intensity matrix, we know that qxy is just cxy. That's the limit of p epsilon xy over epsilon when epsilon goes to 0. And so equivalently, we can say that p epsilon xy, the term that appears here, should scale like epsilon. And in fact, that's equal to epsilon times qxy plus little o of epsilon. Little o of epsilon is any function that is small compared to epsilon. Okay? So that's the first thing we can say. And then also you see that we have this p epsilon xx that need to be re-expressed but using the transition matrix. Notice that p epsilon xx is probability of staying in state x, so that's 1 minus the probability that we jump from state x, 1 minus the sum of the p epsilon xz, but this minus this sum is exactly plus epsilon qxx plus a little o of epsilon for the same reason as before. This is the rate at which we jump from state x, not the rate but the probability, but then the rate is equal to exactly this divided by epsilon, and so that tells you that this indeed must be of the order of epsilon qxx plus little o of epsilon. All right, so we need to prove the result, the different ingredients in blue, convergence almost surely here, this probability here, and also expression of the p epsilon xx or p epsilon xy, but using the coefficient of the intensity matrix. So I'm going to recall the three things we just explained here that we just proved. These are here. And now we want to deduce this first equation here. So for that, I'm going to first do the following. Notice that if you look at this event, to understand this time t, what you need to do in comparison is understand the time sigma epsilon. The way you extract this event, sigma epsilon equals epsilon n, from this event is by summing over all possible state y different from x. Notice that this is by definition the time of the first jump of the epsilon skeleton, so this state must be different from x. If you look at the union over all y different from x of those events, that forms a partition of the set of realization. So indeed, when you look at the union of those events over all y different from x, you get exactly this event here. Sigma epsilon equals epsilon n. For that reason, the way you can study the time of the first jump is by summing expression number 2 here over all y different from x, and you obtain exactly that the probability of this event starting from x, of this event here, is going to be equal by point number 2 to the sum over y different from x of those probabilities here. So we have p epsilon xx at the power n minus 1 times p epsilon xy. And then notice here that this term here depends on x n minus 1 but not y. The sum is over y. So you can extract that's this term. And then if you look at the sum over all y different from x of p epsilon xy, that's exactly the probability that in the next epsilon unit of time, you are going to jump from state x. So that's exactly 1 minus the probability that you stay in state x. This sum here without this term would just be 1 minus p epsilon xx. All right. So now using point number 1, you can say that the probability that t is larger than u, given that we start from state x, is the same as the analog event for the time sigma epsilon. And so using this convergence almost surely, you can deduce that the probability that t is larger than u by point number 1, especially this part here, is equal to the limit when epsilon goes to 0 of the same probability, but this time sigma epsilon larger than u. Okay? And I'm just going to write u as epsilon times u over epsilon to underline the fact that sigma epsilon in fact is a multiple of epsilon. Alright, so then after you can use again point number 2 and say that we have here. Notice the blue term here is the same as here. So I'm using this. This is the limit when epsilon goes to 0 of, so the probability that sigma epsilon is larger than this, okay, is exactly the probability that sigma epsilon is equal to n or n plus 1 or n plus 2 and so on for, all n larger than u over epsilon. So you can write this event that way. I'm just saying that larger than this means equal to this or this plus 1 or this plus 2 and so on, and the fact that those events are mutually exclusive, and so eventually you obtain this sum here. Now look carefully at this sum. You have n larger than this term. I can extract the first term here. That's going to give me a limit when epsilon goes to 0 of the first term in this sum here would be p epsilon xx at the power u over epsilon. And what's left in the sum is, well, the same blue term, but now I start the sum from n equals 0. And now this sum, in fact, is extremely simple. Even if epsilon is small, and so p epsilon xx is close to 1, this is still strictly less than 1. So the infinite sum of the p epsilon xx at the power n is equal to, it's a geometric series, so the limit is equal to 1 over 1 minus the ratio. In this case, that's 1 over 1 minus p epsilon xx. But we have exactly a 1 minus p epsilon xx here. So this tells us that this whole sum, in fact, is just equal to 1. And we end up with the fact that this probability that we are looking for is just equal to the limit when epsilon goes to 0 of p epsilon xx at the power u over epsilon. So now notice that u over epsilon when epsilon goes to 0 goes to infinity. So the power here goes to infinity. But what's inside the parenthesis here, it's p epsilon xx when epsilon is very small, this is close to 1. Something very close to 1 at the power something very large is undetermined. And the way you really understand that is by taking the log of this expression. You just said that the log of this is u over epsilon times the log of this probability. But now you go back to point 3 and you say the p epsilon xx is equal to this expression. And the log of that is, when epsilon is small, of the order of epsilon qxx. And from that, you can deduce the limit of this term, and you get exactly exponential. So more precisely, limit when epsilon goes to 0, this is equal to limit when epsilon goes to 0 of 1 plus epsilon qxx at the power u over epsilon. This scales like epsilon, this scales like 1 over epsilon. Multiplying the two, the epsilon disappear. And so in the limit, eventually, you can prove that you get exponential u qxx. And that indeed gives you the first result. All right, so then this answers the question when, after an exponential amount of time with rate minus qxx. Now to answer the question where, we are going to follow the same reasoning, but instead of summing 2 over all y different from x, I'm going to sum 2 here over all n larger than 1, because sigma epsilon must be equal to either epsilon or 2 epsilon or 3 epsilon and so on. The union over n larger than 1 of the even sigma epsilon equals epsilon n is a partition of the set of realization. And so looking at this union, I'm indeed going to extract this term, keep only this one. And so summing over all n different from 0, we are going to extract this event. Okay? So we do this first. Sum 2 over n. The probability of this event is exactly equal to the sum over n of those events that are equal to those, so that gives you this expression, okay? Now notice that this time, because the sum is over n and not y, this term can get out of the sum. At the opposite, this term here stays in, but this is exactly the sum for n equals 0 to infinity of p epsilon xx at the power n. Here, the n starts from 1. If I start it from 0, we have an n here instead of n minus 1. And exactly like we argued before, this is the infinite sum of a geometric series. This is equal to 1 over 1 minus the ratio. That's 1 over 1 minus p epsilon xx. And that gives you this expression. This probability is just equal to p epsilon xy divided by 1 minus p epsilon xx. And then from that we can conclude a little bit like before. Now, using 1, we can say that the value of the process at time t, of the continuous time process at time t, is the same as the value of the epsilon skeleton at this time, sigma epsilon over epsilon. We can use this take the limit when epsilon goes to 0, and then use 0.3 to have a more explicit expression, and it gives us the following. So yeah, first I'm going to write this more explicitly using 0.3. It's only after that I'm going to use 0.1. Notice that from 0.3 we have that p epsilon xy is about equal to epsilon qxy plus a little of epsilon, and then 1 minus p epsilon xx that is here, so 1 minus that is indeed equal to epsilon qxx plus little of epsilon. That gives me this expression, and then now using taking the limit as epsilon goes to 0 and using this convergence almost surely, now we use the second one here, we get that the probability starting from x that xt equals y is the same as the probability starting from x that the first time the epsilon skeleton jumps is to go to state y. That's true only in the limit. But then this probability by the previous point is equal to that. So we take the limit when epsilon goes to 0 of this blue term. Now notice that when epsilon goes to 0, this little of epsilon disappears. It's negligible compared to the epsilon here. Same here. So eventually in the limit you get minus epsilon qxy divided by epsilon qxx, sorry. And of course the epsilon simplify, and you get minus qxy divided by qxx here. That's exactly this expression here. So that shows the theorem. Now let's look at an example of a continuous time Markov chain with explosion, meaning that the process jumps infinitely many times and also converges to infinity in a finite amount of time. But before talking about this counterexample, let's go back for a minute to this theorem, and I want to argue that this theorem indeed gives us an explicit construction of the process. So the reason for that is that if you go back to the definition of the dynamics of the process in terms of transition rates, those transition rates are limits when epsilon goes to 0. They are not only difficult to conceptualize, but it's difficult for a computer, for instance, to handle such limits. And so simulating a continuous time Markov chain using the definition of transition rates and intensity matrix can be tricky, but it's much easier to simulate the process using this result. So for instance, assuming that the process starts in state X, you would tell your computer, stay in state X for an exponential amount of time with parameter minus qxx, at which time you jump to a new state. This new state is state Y with probability minus qxy over qxx. A computer can very easily simulate an exponential random variable and can also very easily compute those or simulate those probabilities much more than dealing with transition rates that are kind of limits. All right, so now this gives us an explicit construction of the process at all time if everything goes well. But it's possible that there is explosion of the process, in which kind you can only construct the process until this time to explosion. So let's define this notion here of time to explosion. So we have from this theorem an explicit construction of the process until potential explosion. To define the notion of explosion, let's call tau n the time of the nth jump of the process. Obviously, tau n is less than tau n plus 1. You have to wait more time to have n plus 1 jumps than n jumps. And so the sequence tau n is increasing. And so in particular, it has a limit when n goes to infinity of tau n that can be finite or infinite. We say that the process explodes, or this is a process with explosion, if this limit that I'm calling tau infinity, that's a random time, is finite. Okay, so you understand that in order to have explosion, we need to have states for which the rate of jump is higher and higher and higher and arbitrarily large. And so to indeed have explosion in the context of continuous time Markov chain, we need to have an infinite state space. So to build our example, I'm going to start with a state space equal to the set of non-negative integers. And I'm going to assume that we jump from integer n to the next one, n plus 1, at rate mu times n at the power alpha. Notice that I only precise this rate. This means that from state n, you can only go to state n plus 1. And so the embedded Markov chain associated to the process, in fact, is not really a stochastic process. That's something that is more deterministic. Starting from state 1, the process is going to go to state 2 with probability 1, and then 3 with probability 1, and then 4 with probability 1, and so on. So the embedded Markov chain is deterministic, but the times of the jumps are still weights, and so exponentially distributed and random. All right, so now let's look, before we look at an example of process with explosion, let's look at a particular case, the case when alpha equals 1. This case is interesting, that has a nice interpretation in biology. This process is called the Yule process, okay, and can be interpreted as a model for cellular division. So, to understand in this process the rate at which we go from n to n plus 1, let's assume that we have n cells. Now the state corresponds to number of cells. So we have n cells, and let's assume that mu is the rate at which each of those cells independently is going to divide into two daughter cells. Okay, so we have a rate mu like that attached to each cell, and the time we have to wait to go from n to n plus 1 cells is exactly the time it takes for one of those to divide. And so we have this picture here. Maybe let's say cell number 2 is the first one to divide into two daughter cells, and we go from n to n plus 1 cells. To find the rate of the process here, so clearly we go always from a state to the next integer. The goal is to find the amount of time it takes for this population of cells to give birth to a new cell. And the way you can think of that is just to say that you can think of each of those n cells as exponential clocks with rate mu that are independent. And then the first clock that is going to ring is going to tell us the next time at which there is a cellular division. All right, so all those clocks are exponential with parameter mu. There are n of them, and they are independent. And so by the superposition property, the time of the next jump, the next time at which we have a cellular division, so the time at which we go from n to n plus 1, is going to be equal to the time at which one of those clocks rings, which is the minimum of n exponential random variable with parameter mu by the superposition property that's exponential with parameter mu n. Okay? And so that gives you indeed that we go from n to n plus 1 at rate mu n. Okay? And that corresponds indeed to the special case where alpha equals 1. Now, it turns out that for this process, indeed, the population size goes to infinity. It in fact goes to infinity exponentially fast, but still it will take an infinite amount of time to reach infinity. And so this process for alpha equals 1 is not a continuous time Markov chain with explosion. But if we assume that alpha is strictly larger than 1 in the definition of the rate here, then in this case, you can prove that the time it takes to go to state 2 and then 3 and then 4 and so on are shorter and shorter, and they go to 0 fast enough so that the time it takes to converge to infinity is finite, equal to some time to infinity that is finite with probability 1. So the way you prove that is by using the monotone convergence theorem. I'm just going to say that starting with state 1, or you can think one cell, but we are not in the case of the Yule process, those cells they reproduce faster, then the expected value of this time, to infinity, the time it takes to have infinitely many jumps, is going to be equal to the expected value of this infinite sum. Those times Tn are here. It's T1, T2, T3, and so on. In general, Tn is the time between jumps. That Tn is exactly going to be the time it takes to go from state n to state n plus 1. Okay? So, to infinity clearly is equal to this infinite sum of Tn. Okay? Now, because those times are positive, you can think of the infinite sum as the limit of the sequence of partial sums, but the sequence of partial sum is monotone, and so you can think of that as a monotone limit and use the monotone convergence theorem to say that expected value of the infinite sum is equal to the infinite sum of the expected values. Now, those times Tn, we understand them perfectly, they are written here. The process jumps from n to n plus 1 at rate mu n at the power alpha. This means that in this case, for this specific process, Tn is exponentially distributed with parameter mu n at the power alpha. The expected value of this exponential random variable is equal to 1 divided by the rate. That's 1 over mu n at the power alpha. And then eventually, you get that the expected value of tau infinity is the infinite sum of 1 over mu n at the power alpha. When alpha, so mu is fixed, okay? But n goes from 1 to infinity. When alpha is strictly larger than 1, this infinite sum is finite. At the opposite, if alpha equals 1, like in this case, or alpha less than 1, then this infinite sum is infinite. We do not have explosion. But when alpha is larger than 1, the cellular division is too fast, and in this case, expected value of tau infinity is finite. Because tau infinity has a finite expected value, it must be almost surely finite. So that means that with probability 1, tau infinity is finite, and so we have explosion of the process in a finite random time. All right, so going back to this result, this tells us that we can use a computer or have a nice interpretation of the process, and we can construct the process explicitly even when alpha is larger than 1, but of course we can only construct the process until some random time, to infinity. After that time, the process is no longer defined. So now let's define the notions of communication classes, irreducibility, transience, and null and positive recurrence. These are key concepts to understand the limiting behavior of the process. So we say that two states x and y communicate if we can go from x to y and from y back to x in a finite amount of time that I'm calling S and T here, both with positive probability. The definition is exactly the same as in discrete time covered in chapter 7, except that obviously now those times S and T or time increments are real numbers instead of integers because we are in continuous time. From this, we can also define the notion of irreducibility. We say that the process is irreducible if it has only one communication class, same definition as in discrete time. Now, in chapter 7, we saw that to easily check whether states x and y communicate, we use some kind of visualization of the dynamical structure of the process by drawing some directed graph showing whether we can go from one state to another. This directed graph was defined by starting with vertex set, which is the set of states, and then we would draw an arrow from x to y if and only if pxy probability of jumping from x to y is strictly positive. That was the definition in discrete time. Now, because we are in continuous time, instead of using the one-time step transition probabilities to define the evolution or the dynamics of the process, we use instead the transition rates. And in this case, we are going to define the graph by drawing instead an arrow from x to y if and only if cxy, the rate at which we jump from x to y, is strictly positive. So this graph can again be used to easily find states that communicate and eventually the communication classes. So the way you would do that is just say that let's assume that you can find a sequence of states starting from x and up to y such that the rate of jump from one state to the next one is strictly positive, then this would clearly imply, if it's the case, that indeed you can go from x to y in a finite number of jumps, okay? All happening with positive probability at a positive rate, and so you can indeed go from x to y in a finite amount of time s, right? So the existence of S such that Pxxy is positive can be visualized in the graph by a path of arrows going from X to Y. Right, maybe not one arrow, but a path of arrows. You might need a sequence of jumps for that. And from this property, you can easily deduce that two states communicate, X and Y communicate, if and only if their directed path in your directed graph, one going from X to Y and one going from Y to X. Or you can also think of that as a directed cycle that contains X and Y. That's the same characterization as in discrete time, except that now arrows are not where Pxy is positive, but where Cxy, the rate, is positive. All right, so now, the next thing we are going to see is that, in fact, the continuous time Markov chain and its embedded Markov chain that we define in the first result we proved in this video, in fact, have the same directed graph and so the same communication classes. And to see this, just notice that the probability that the embedded Markov chain goes from X to Y, Pxy, in this case P bar, xy, I change the notation to differentiate from probability for the continuous time Markov chain. So this probability, this is what we proved at the beginning of this video, is equal to the rate at which we jump from x to y, divided by this sum, which is exactly the rate at which we jump from state x. Now, because we assume that our continuous time Markov chain is a conservative system, this sum here is in fact finite. The rate at which we jump from state x is finite. We do not have instantaneous jump. And so, because this is finite, eventually you can deduce that the probability of going from x to y for the embedded Markov chain in one time step is strictly positive if and only if Cxy here is strictly positive. Which means that the directed graph that describes the dynamical the dynamical structure of the continuous time Markov chain is the same as the directed graph that describes the dynamical structure of the embedded Markov chain. And so from this, we can conclude that because clearly whether x and y communicate or not can be viewed from this point of view here. We have a directed cycle containing x and y. We deduce that xt and yn, the embedded Markov chain, must have the same directed graph, and so they must have the same communication classes. So from this, we can deduce that, in particular, the process xt, the continuous time Markov chain xt, is going to be irreducible if and only if the embedded Markov chain is irreducible. To understand the notion of communication classes and irreducibility, you only need to look at the embedded Markov chain, and you can just use the result we saw in chapter 7. Now, let's define the notion of transience, null recurrence, and positive recurrence. So the definition, again, is the same as in discrete time. We have, let's say, a state y. And so this time ty that appears here is the time of return, of first return to state y. We say that state y is recurrent if starting from state y, ty is finite with probability 1. This means that starting from state y, we are going to return to state y in a finite amount of time. This is the definition of recurrence that we have here and here. Transience means that starting from state y, there is a positive probability that ty is infinite, meaning there is a positive probability that we'll never return to state y. And the distinction between positive and null recurrence for recurrent states can be defined exactly the same way as for discrete time Markov chain. Instead of looking at whether this time ty is finite or not with probability 1, instead we look at the expected value of this time, again starting from state y. If the time it takes to return to state y is finite, but also stronger assumption than that, finite on average, then we say that the state is positive recurrent. If at the opposite, the time it takes to return to state y is almost surely finite, but does not decay to 0 fast enough so that the expected value is finite, and then in this case, the expected amount of time is going to be infinite. In this case, we say that the state is null recurrent. The definition is the exact same as in discrete time, with one little exception. That's if you look at the definition of time ty. In discrete time, ty, the time of first return, was defined as the infimum of n strictly positive, because we are on the integers, n strictly positive means n larger or equal to 1. So infimum of n strictly positive such that xn equals 1. Okay? In this case, if we mimic this definition and simply take the infimum of t larger than 0 such that xt equals y, because starting from state y, the process is not going to jump immediately to another state and stay in state y for a little bit, then this time would always be 0. Okay? What we need to do in the definition is impose an extra condition, which is the fact that now ty is not going to be the smallest time t such that xt equals y, but that's going to be the smallest t such that not only xt equals y, but also xt minus, which is the state right before time t, is going to be different from y. So what we do here is basically we just say starting from state y, a tiny bit after that time, so again there is no successor in real time, so a little bit after that time we are still in state y. So what we do is we let the process jump somewhere else, and we define time ty as really the next time we return to y, and so we jump from another state to state y. That's the way the time of first return is defined. The definition is slightly different than in discrete time, because in discrete time, starting from state y at time 0, you can be at the next time step somewhere else, while here, because there is no next time step, slightly before time 0, you are still in state y. That's why we need to change slightly this definition. Except for that, using this new definition, you can define positive recurrence, null recurrence, and transience the same way as for discrete time Markov chain. Now notice that if a state is recurrent for the continuous time Markov chain, then the number of visits in this state is going to be infinite, starting from this state. And clearly, if the continuous time Markov chain visits a state infinitely often, then the embedded Markov chain also is going to visit this state infinitely often. At the opposite, if a state is visited only a finite number of times in continuous time, then the embedded Markov chain also is going to visit this state only a finite number of times. From this, we conclude that the continuous time Markov chain and its embedded Markov chain, from the definition, must have the same recurrent state and transient states. Now, at this point, you see that the two processes, continuous time Markov chain that we are trying to understand and the embedded Markov chain that we know better from result of chapter 7, those two processes, in fact, have the same communication classes. They also have the same recurrent and transient states. Now, because we know that recurrence and transients are class properties for the discrete time Markov chain, we can deduce easily that recurrence and transients also must be class properties for the continuous time Markov chain. So I remind you, this is a notion I defined in chapter 7. Saying that recurrence and transients are class properties means that if x and y communicate, then they both must be recurrent or they both must be transient. The way you can transport the result from discrete time to continuous time is easy in view of those two properties. Let's assume, for instance, that x and y communicate and that, for instance, x is recurrent. For the continuous time Markov chain, to prove that we have a class property, we need to prove also that y is recurrent. For that, you just say, because the two processes have the same communication classes and recurrent state, then x must also be recurrent for yn, and x and y must also communicate for yn. Because recurrence is a class property for a discrete time Markov chain, we deduce that y must be recurrent, but because the two processes have the same recurrent state, we deduce that y recurrent for yn also implies y recurrent for xt. And so conclusion, if two states communicate, one recurrent means that the other one is recurrent. Also, if one is transient, the other one is transient. Eventually, we conclude from well-known results that we already proved previously for discrete time Markov chain that recurrence and transients also are class properties for the continuous time Markov chain. Now, notice at the opposite that the expected value of the time of return, called the mean recurrence time, might be strongly different for the continuous time process xt and the embedded Markov chain. This is due to some kind of distortion of time. It's possible that the process xt jumps at some very, very high rate. If the state space is infinite, those rates can be arbitrarily large. And so the process can return to the same state in an amount of time which is finite on average, but it's going to take an infinite amount of time on average for the process yn to return to that state. And so I'm concluding this slide with this remark. It turns out that the two processes, xt, continuous time Markov chain, and embedded Markov chain, have the same communication classes, recurrent state, transient state, but they might not have the same positive recurrent or null recurrent states. And like I told you earlier, at the end of this video, I'm going to give you an example of continuous time Markov chain, xt, that is positive recurrent, but such that the embedded Markov chain yn is not positive recurrent, the embedded Markov chain will be null recurrent. To understand the limiting behavior of the process, the next step is to define and study the stationary distribution of the process. But before, in order to be able to study those stationary distributions, we need backward and forward Kolmogorov equations. to define those equations that are ordinary differential equations, the first step is to prove Chapman-Kolmogorov equations. Those ones are simple. They say that for all states x, y, and times t and s positive, pt plus s xy is equal to the sum over z, all state z of the process, of pt xz times ps zy. The proof is simple. You just have to condition on the state of the process at time t. So I'm looking at this collection of events, xt equals z for all state z. This collection of events form a partition of the set of realization. That's all the possible states of the process at time t. I can condition on this partition, and this tells me that pt plus s xy, probability of going from state x to state y in t plus s units of time, is just the sum over z, I'm conditioning on this partition, of probability of going from x to z in t units of time, then z to y in the next s units of time. This term here is just probability of going from x to t in t units of time. It's pt xz. This one, probability of going from z to y in s units of time. The time t does not matter, it's just ps zy. And eventually, you get indeed this expression here. All right, so using this, we can now state and prove backward Kolmogorov equation, which says the following. So this says that pt prime is equal to q pt. In this expression, q is the intensity matrix of the transition rate, except on the diagonal, it's minus the rate at which you jump from the state. pt is again a matrix with the same size as q. pt is in fact the matrix of the pt xy. The coefficient xy of the matrix pt is just pt xy, probability of going from x to y in t units of time. So this is an ordinary differential equation. Derivative of pt is equal to qpt. Here the derivative means time derivative, and the derivative of the matrix is just the matrix of the derivatives. That's just the way it's defined. So that's an ordinary differential equation, but written in matrix form. It's exactly the same as saying that we have equation coefficient by coefficient, and so for all states x and y that might be equal or different, we have that pt prime x y is equal to qpt x y. All right. So to prove this result, the first step is to understand the derivative here, or the derivative of pt xy. For that, let's return to the definition of derivative. Okay, the derivative with respect to t of pt xy is just going to be the limit when epsilon goes to 0 of pt plus epsilon xy minus pt xy divided by epsilon. So to be able to understand that limit, the first step is to try to understand pt plus epsilon xy and try to express that using pt xy. That's the idea of the proof. So first, we are going to do the following. I'm going to start from x. I end up at y in t plus epsilon unit of time. And to be able to express pt plus epsilon xy using pt xy, I'm going to condition on all the possible states z at time epsilon. And use Chapman-Kolmogorov equation that we just proved here, but instead of having those two time increments, ts, now the time increments are epsilon and here t. If we write Chapman-Kolmogorov equation, in this case, we obtain the following. And I'm precising here, I'm going to explain why, that we only prove the result when s is finite. The result is still true when s is infinite and the system is conservative, but the proof is way more complicated. I'm going to explain why after. So first, let's look at pt plus epsilon xy. By Chapman-Kolmogorov equation, that's equal to the sum of P epsilon xz times pt zy. That's what you find here. That's how I decompose my time here. Epsilon first, t after. Then notice that if you look at this sum, P epsilon xz, typically when epsilon is small, and that's the idea you have to have in mind, eventually we take the limit when epsilon goes to 0. When epsilon is small, P epsilon xz is small also when x and z are different. Okay, the probability of a jump from x to z in a very short time interval has a very small probability. At the opposite, if x and z are equal, in which case this becomes P epsilon xx, then this term becomes close to 1. Okay? The probability that we stay in state x in this very short time increment should be close to 1. So the behavior of those terms depends really on whether x is equal or different from z. So to really understand those terms, I'm going to split the sum into two pieces. The sum over all z different from x, and then one last term, which is the term for z equals x. Now, P epsilon xz and P epsilon xx take two different forms, depending on the coefficient of the intensity matrix. So remember that this, by definition, should be of the order or close to the rate at which we go from x to z times epsilon. So this is about epsilon times qxz. At the opposite, this term is close to 1, and using, again, like the connection between those P epsilon xz xx and the coefficient of the intensity matrix, we obtain the following. This is the same properly as what we used in the proof of the first result in this video. This is just epsilon times qxz plus something negligible compared to epsilon, Liddell law of epsilon. This one at the opposite is equal to 1 plus epsilon qxx plus Liddell law of epsilon. Now, you see that here we have a sum over z different from x. We don't have a complete sum over all states. If we want to have a complete sum here, the missing term, that is like the blue term here, but for z equals x, would be epsilon qxx times pt xy. But these terms appear here again. It's epsilon qxx times pt xy. So step 1, we split the sum into two pieces, and now what we are going to do at the opposite is put back together those terms. I'm going to put the blue product here back inside, okay, with the Liddell law of epsilon, and that's going to give me a full sum of epsilon qxz plus Liddell law of epsilon pt zy, now for all z in S, not only z different from x, but then the term remaining is this 1 times ptxy. Okay, so eventually this is equal to ptxy plus the same sum as here, but now the full sum. Okay, so we have this expression here, and notice now that this term minus this one is just equal to this sum. We want to look at this minus this. To look at the derivative, we want to look at pt plus epsilon xy minus ptxy and divide by epsilon. This minus this divided by epsilon is just this sum here divided by epsilon, that like this epsilon eventually is going to disappear. Liddell law of epsilon over epsilon goes to 0 when epsilon goes to 0, and so eventually the derivative, this minus this over epsilon when epsilon goes to 0, is equal to this sum here. Okay, so that's the result we get. Eventually the derivative here is equal to the limit when epsilon goes to 0 of that. This simplifies, we only get this sum, and notice that this is exactly, this sum here is exactly the scalar product of row x of the matrix Q and column Y of the matrix PT. The this scalar product is exactly, by definition, a coefficient xy of the matrix QPT. So we indeed have that for all x and y, PT prime xy equal to QPT xy. So that shows backward Kolmogorov equations. Now, I precise at the beginning that we only prove the result when S is finite. And it's not obvious where we use the fact that S is finite. We use it to go from this step to this step. Here you see that we have a sum over all z different from x of a term with a little o of epsilon. Okay? And then at the next step I put the little o of epsilon outside the sum. I can do that if the sum is finite. Little o of epsilon means something small compared to epsilon. If I have a finite number of those things and I add them up, that's still small compared to epsilon, when epsilon is small. But if the sum is infinite, an infinite sum of little o of epsilon might not be small compared to epsilon. Now, it turns out that even if S is infinite, this sum of little o of epsilon is again going to be small compared to epsilon, but the proof is way more technical. And to indeed justify this step, we need to use the fact that the system is conservative. And the proof is way more technical. So I'm going to skip that. Here you have the spirit of the proof. The proof in the case where S is infinite is the same, except that there is an extra step that is a little bit tricky. All right, so this is backward Kolmogorov's equation. Forward Kolmogorov's equation say almost the same thing. It says that now this time PT prime is equal to PT times Q. Again, that's an ordinary differential equation in a matrix form. That means the same as for all x, y, two states, PT prime xy is equal to PT times Q xy. It's exactly the same result, except that now, instead of looking at the product Q times PT, we look at PT times Q. Notice that when you have matrices, it's not clear that things commute. The product of matrices typically is not commutative. Okay, so this result is not obvious. Forward Kolmogorov's equation doesn't clearly follow from backward Kolmogorov's equation. In fact, even if one does not imply the other one, because matrices do not commute typically, the proof is the same, except that now what we are going to do is, instead of conditioning on the state of the process at time epsilon, we condition on the state of the process at time t. Instead of having the division epsilon then t, now we have t then epsilon. The calculations are the same as before, except that somewhere PT and Q get exchanged in the calculation, and here is again the proof. I'm not going to comment on that. This is the exact same proof as before, but if you write the details, you will see that terms are exchanged, and so eventually you get PT times Q instead of Q times PT. All right, so now if you combine backward and forward Kolmogorov equations, we get the following. We get that PT prime, the derivative, the time derivative of PT, is equal to QPT, which is also PT times Q. So Q and PT commute, which is not obvious. And from this equation in matrix form, you can in fact deduce, at least in theory, an expression for the derivative of PT. So the idea is exactly the same, even if you deal with matrices. The idea is exactly the same as if you deal with a function with value in R. Okay? If we had f prime t equals q times f of t, then clearly f of t is of the form e at the power qt. Here, the idea is exactly the same. The solution of this equation is written in matrix form. PT equals exponential of Q times T. The problem is that exponential the function exponential is well known, but the exponential of a matrix is not clear. So next step is, how do we define the exponential of a matrix? Well, you just look at the exponential function. You know that e to the x is equal to the infinite sum of x at the power n over n factorial. That's written the exponential in the form of a power series. And so you can write e to the x using the power of x. Now the power of the matrix Q are well defined. And that's the way you define the exponential of a matrix. You just say that the solution of this differential equation is of this form: pt is equal to e at the power q times t, okay? And this exponential of a matrix is again a matrix which is equal to the infinite sum over n of qt at the power n. So q at the power n times t at the power n. Q at the power n is well defined. You can multiply matrices as long as they have the same size, divided by n factorial. So you use the power series representation of the exponential to be able to define the exponential of a matrix. So backward and forward Kolmogorov equation gives you an explicit expression of the derivative of pt, and so an explicit solution of pt. But obviously, to find explicitly the form of that in practice, you will need to find all the powers of the matrix Q, okay, which looks extremely complicated. So this equation is kind of the analog in discrete time of the fact that the probability of going from x to y in n time step is the coefficient xy of the matrix P, transition matrix at the power n. We saw that in chapter 7. This is a nice representation. The problem is that in general, P at the power n cannot be computed easily. We are faced with problem with linear algebra. Here, the problem is the same. Computing Q at the power n for all possible n is too complicated in general in practice. And so this result has only some value in theory, but not really in practice. And so in particular, now we are going to use this differential equation here, backward and forward Kolmogorov equation, to be able to study the stationary distribution. And in fact, using those differential equations, we can prove that pi is stationary if and only if pi q equals 0. So here is the definition of stationary distribution for a continuous time Markov chain. We say that a probability measure pi on the state space S. So think of pi as a row vector with coordinate pi x for all x in S. We say that this distribution or probability measure is stationary for the process xt if p sub pi xt equals y is equal to pi y for all state y and for all time t. P sub pi is a short for a conditional probability. That's the probability given that x0 is distributed according to pi. This means that x0 is equal to little x with probability pi x. So this equation tells you that given that we start from the distribution pi, the distribution at time t is again going to be pi. In other words, if you start from the distribution pi, or if at any time the process reaches the distribution pi, then it's going to stay distributed according to pi for any future time, any time in the future. And so you can think of pi as some kind of fixed point, but it's a fixed point in the set of probability measure on S. So reaching the stationary distribution means that the distribution is not going to change, but that doesn't mean that the process becomes static. The process still evolves, but the distribution is fixed and is not going to change. So this is the definition of stationary distribution. This concept is important because when dealing with a continuous time Markov chain xt that is irreducible and positive recurrent, then we can prove existence and uniqueness of this stationary distribution pi, and this distribution is going to describe the limiting behavior of the process. In particular, that's by using this distribution that you can find the fraction of time spent in a state y, and also the probability that the process is in state y at some large time t. That's why this concept is important. Now, to compute pi, to find pi in practice, the main tool is the following theorem that can be proved using backward and forward Kolmogorov equation. The theorem says that pi is stationary and so satisfies this equation for all yt if and only if pi q equals 0. Q here again is the intensity matrix, and so to find pi you just have to solve a linear system. Pi q equals 0. The proof follows from Kolmogorov's equation that I remind you here, and you can think of this theorem as the analog in discrete time of the theorem that says that pi is stationary if and only if pi p equals pi, where p is the transition matrix. This is the analog of this theorem, but in discrete time for discrete time Markov chain. So, to prove this theorem, we are going to first look at this equation here. We are going to first prove that this probability that we find here also, starting from pi, the probability that xt equals y should be equal to pi pt y. Remember, pt is this matrix of the pt xy. Okay, so this is the product of a row vector and a square matrix with the same size. So this equation is true for any probability measure on S. That's not only true for a stationary distribution. And so what this tells you more or less is that multiplying the vector pi by the matrix pt is exactly the same as applying t units of time of the Markov chain starting from the distribution pi. That's what this equation says. This is equal to the probability of being in state y at time t, or distribution in general of xt at time t, given that we start from the distribution pi. So the proof is easy. We just have to condition on the initial state of the process. Okay, so I'm just looking at all the possible initial value of the process. So condition on the sum over x with those events x0 equals little x. We have exactly sum of the probability of this event given that we start from x times the probability that we start from x. Now, by definition, this piece of pi means that we start from x with probability pi x. So this probability is just pi x. And this is exactly the probability of going from state x to state y in t units of time. That's exactly the coefficient xy of the matrix pt. And so eventually we find sum over x of pi x times pt xy. This is exactly the scalar product of the row vector pi. Think of, again, this probability measure as a row vector. And with size the number of states, so pi x times ptxy, column y of the matrix pt, that's the scalar product of those two vectors, and that's exactly the coordinate y coordinate of the vector pi times pt. All right, so now notice that, again, this is true for any probability measure, but if we assume that pi is stationary, then this is equal to that. This is pi y. So this is pi y for all t. So this means that pi pty is equal to pi y, and so pi pt equals pi. So that's a characterization of a stationary distribution. From this calculation, that is true for any probability measure, we can deduce that pi is stationary based on the definition if and only if pi pt equals pi. That's the first ingredient to prove that pi is stationary if and only if pi q equals 0. Now, the other main ingredients to prove this equivalence are, again, backward and forward Kolmogov's equation. So first, let's assume that pi is stationary. So according to this calculation, like I just explained, this means that pi pt is equal to pi for all t. And then let's check that indeed, in this case, pi q is equal to 0. So we start by looking at pi q. Then, because pi pt is equal to pi, I can replace pi by pi pt. Okay? So I have product pi pt on one side and q on the other side. Now, the product of vectors matrices is associative. It's not always commutative, but it's associative. So I can move the parentheses here and say that it's pi times pt times q. Okay? But pt times q is the expression here that appears in forward Kolmogorov equation. We know that pt times q is equal to the derivative of pt, and so using forward Kolmogorov equation, I can say that this is equal to pi times pt prime. Now, you can think of pi, because that does not depend on time t, as like a constant. So the pi times the derivative of pt is the same as the derivative of pi pt. Eventually we get pi pt prime. But because, again, pi pt is equal to pi, I'm using again this equation here. I used it here, I'm using it here again. Because pi pt is constant equal to pi for all t. This is just pi prime, but pi does not depend on t. So its derivative, its time derivative is just equal to 0. So that shows that indeed, if pi is stationary, pi q is equal to 0. To prove the converse, we are going to instead use backward Kolmogorov's equations, and the proof is like that. Now we assume that pi q equals 0. Because pi q equals 0, again, I can redo those calculations, but going backward. I start now with this term, pi pt prime, for the same reason as before, that's equal to pi pt prime. I can just move the derivative. Then, using now this time backward Kolmogorov equation, we know that pt prime is q pt. So now this time we have pi times qpt. The reason for using backward Kolmogorov's equation instead of forward Kolmogorov equation is because now I want a q right next to the pi to be able to use that pi q equals 0. Again, I can use the fact that the product of matrices is associative to move the parentheses. That gives me pi q times pt. This is 0, so the product is 0. So this tells us that pi pt, the time derivative of pi pt, is equal to 0. So pi pt must be constant, must not depend on time. And so in particular, that's equal to pi p0. But p0 clearly is the identity matrix. That's the probability, that's the matrix, the coefficient xy of this matrix would be the probability that x0 equals y given x0 equals x. That's clearly equal to 1 if x equals y, but 0 if x is different from y. So pi 0 is the identity matrix. Multiplying a vector by the identity matrix does not change the vector. That's again pi. Conclusion, if pi q equals 0, pi pt equals pi, this is exactly the definition of stationary for a distribution according again to this equation we proved here. Alright, so that shows the theorem. Pi is stationary if and only if pi q equals 0. This is extremely useful in practice. That's typically how you find the stationary distribution. In some cases, solving this system is difficult, and there is a trick that you can use sometimes that doesn't always work. The idea instead is to find a reversible distribution, and we know that if from this theorem, we can prove that if a distribution is reversible, then it must be stationary. That's the last result of this slide. Let's assume that pi is a reversible distribution. The definition here is just saying that pi x qxy is equal to pi y qyx. In discrete time, the definition was the same, except that instead of q, we had p, the transition probabilities. So if this is true, if we can indeed find a distribution pi such that all those equations are true for all x and y, then we can prove that by definition this means that pi is reversible. Then we can prove also that pi is stationary. The proof follows from this result here. The reason why this is useful in practice is because in some cases, at least when there is a reversible distribution, it's possible that pi q equals 0 is a linear system that is very difficult to solve, while finding pi satisfying those equations, called detailed balance conditions, is easier. So the proof that pi reversible implies pi stationary is here at the bottom. We use this theorem. To be able to prove that pi is stationary, we just need to prove that pi q equals 0. The trick is the same as in discrete time. We start with pi q x. We look at this quantity. By definition of product of a vector and a matrix, that's going to be the sum over y of pi y times q y x. Q y x are the coefficients of the matrix Q. Now you see that in this sum, I have a term here that depends on y and another term here that depends on y, and the sum is over y. So computing this sum in general is difficult, except that because pi is reversible, and so those equations are true, I can replace pi y q y x, this term here, by pi x q x y, and make the term here inside the sum more dependent on x and less dependent on y, which should make things easier. So indeed, using the detailed balance equation, I get that this is the sum over y of pi x qxy. Now, this pi x does not depend on y, so it can go outside the sum, and so, but the sum over y of qxy is equal to 0. This follows from the definition of the intensity matrix. Remember, at the beginning of this video, I told you that for property of the intensity matrix, the coefficient on the same row add up to 0. That's exactly what we do here. We look at sum of all the coefficients on row x of the matrix. This is equal to 0, so that's 0. So now we can conclude that if pi is reversible, pi q x is equal to 0 for all x, so pi q equals 0, and by this theorem here we deduce that pi is stationary. Using the notions of irreducibility, transience, positive recurrence, and null recurrence, also the concept of stationary distribution, we can now give a complete picture of the limiting behavior of a continuous time Markov chain. So more precisely, we have this theorem that describes the limiting behavior of the process. Two important quantities in this slide are fty and ptxy. I already defined ptxy, that's the probability of going from x to y in t units of time. We want to understand this limiting probability when t goes to infinity. Fty is the fraction of time spent in state y by time t. This is properly defined here. You look at this indicator function that's equal to 1 or 0, 1 as long as the process is in state y. Looking at the integral from 0 to t gives you the amount of time spent in state y by time t, dividing by t gives you indeed the fraction of time spent in state y by time t. And the goal is to find the limit. So the theorem says that if the process is irreducible, so only one communication class, then there are two possibilities. Either all states are transient or null recurrent. In this case, we said that the process itself is transient or null recurrent. in which case there are no stationary distributions, and fraction of time spent in a state and limiting probabilities all go to 0. This can only happen, of course, when the state space is infinite. I also wrote that 0 is equal to 1 over the mean recurrence time. I remind you again that this quantity here is the expected amount of time you need to return to state y starting from state y. So 1 over this is 0. This is the same as saying that this is infinite. This is indeed the case when the process is transient or null recurrent. By definition of transience and null recurrence. So this is the first option. Second option, all states are positive recurrent. And in this case, there is a unique stationary distribution pi. Uniqueness follows from irreducibility. Existence follows from positive recurrence. And in this case, those two quantities here are going to converge instead to pi y. So the stationary distribution is going to describe the behavior of fraction of time spent in a state or limiting probabilities. Those are strictly positive, and also the mean recurrence time, again, expected amount of time you need to return to a state starting from this state, satisfies this equation. Minus 1 over QYY EY TY is equal to pi y. That's how you find the mean recurrence time in practice. You first find the stationary distribution and you look at this equation. So this theorem is almost the same as in discrete time. For discrete time Markov chain, I already proved this theorem from scratch in chapter 7, but only for discrete time Markov chain. Now, I'm not going to prove this theorem from scratch. I'm just going to show some kind of connection between the continuous time process and a discrete time process. That's going to be, again, like at the beginning of this video, the epsilon skeleton. And so the idea of the proof is just to show that the epsilon skeleton share the same properties as the continuous time Markov chain in terms of transient, null recurrence, or positive recurrence, and those conclusions are the same as in discrete time. There are only two exceptions, two differences between discrete time and continuous time. The first one is the fact that you see in this theorem we do not talk about aperiodicity. So remember that in the context of discrete time Markov chain, aperiodicity is very important. This means that all states have period 1. This is an assumption that is necessary to have convergence of those limiting probabilities in the case of positive recurrence. Okay? Now, it turns out that in continuous time, this notion of aperiodicity is not even defined, and in fact, it's not required to have the conclusion, to have convergence of those limiting probabilities, PTXY, and that's going to appear in the proof. In fact, we can prove that the epsilon skeleton is always, for all epsilon positive, aperiodic. Okay? We do not need any extra assumption on the continuous time Markov chain. So in this sense, studying a continuous time Markov chain is a little bit easier than a discrete time Markov chain, even if the concept of continuous time Markov chain is more difficult to conceptualize, because this notion of aperiodicity disappears. This simplifies things a lot. The other difference is in the fact that in discrete time, the fraction of time spent in state y converges to pi y, which is equal to 1 over the mean recurrence time. This extra coefficient does not appear. This is because implicitly in discrete time, we assume that at each visit in state y, the process is going to stay in this state 1 unit of time. That's some kind of implicit assumption, okay? At the opposite, so that's what I'm writing here, in discrete time, 1 visit in y means 1 unit of time spent in y. At the opposite, in continuous time, because the time spent in each state, like the waiting time until the next jump, are random variables, they are random exponential on the variables. The time spent in a state depends on the rate of jump from that state. Okay? So, more precisely, each time the continuous time Markov chain is going to visit state Y, it's going to stay in that state for a time that is exponentially distributed with rate minus QYY. But the expected value of this exponential is exactly equal to 1 over the rate. That's this minus 1 over QYY. Okay? And so that's the second difference. In continuous time, at each visit in state Y, we are going to stay in this state for an expected amount of time equal to minus 1 over QYY. That's why we need this extra coefficient to correct fraction of time spent in a state or mean recurrence time in discrete time, because one visit means 1 unit of time there. The fraction of time spent in a state is indeed the reciprocal of the mean recurrence time. Here we need to correct things because the fraction of time spent in a state is not only measured by the mean recurrence time, this also depends on the expected amount of time spent in the state at each visit. Alright, so except with those two little differences, the theorem is the same as in discrete time. And so the idea of the proof, and I should call that just sketch of the proof because I'm not going to go too much into the details, is again, like at the beginning of this video, to look instead at this process Zn epsilon, called the epsilon skeleton, that's equal to x n epsilon. That's the process that only looks at the continuous time process, but at times that are multiples of epsilon. Now it turns out, and we saw that at the beginning of the video, that this epsilon skeleton behaves closely, like the continuous time Markov chain. And so the idea of the proof is just to say that if the continuous time Markov chain is transient, null recurrent, positive recurrent, then the same is true for this process. Also, the fact that if the process is irreducible, then this one also is irreducible. And also to be able to have, in particular, this conclusion in the positive recurrent case, what we need also is to prove that this process is always aperiodic. Alright, so let's deal with irreducibility and aperiodicity first. If xt is irreducible, then we can prove that this epsilon skeleton not only is irreducible, but is also aperiodic. And so the proof is simple, that's just one line. So the probability that the epsilon skeleton jumps from x to y, have in mind that one time step for the epsilon skeleton, increasing n by 1, means epsilon units of time for the continuous time Markov chain. So the probability of going from x to y in one time step for the epsilon skeleton is exactly the probability that we go from x to y in an amount of time equal to epsilon for the continuous time Markov chain. Now, because the process is irreducible, there exists t such that ptxy is strictly positive. But this also means that you can go from x to y in a finite number of jumps. But because the time between the jumps are exponentially distributed, and those exponential random variables can be arbitrarily small with positive probability, for any epsilon, even small, as long as epsilon is strictly positive, you can prove that p epsilon xx must be positive for all x and y. This implies that the probability of going from x to y in one time step for the epsilon skeleton is always positive. And so the transition matrix of this process is a matrix with only positive coefficients. So that means that in one time step, you can go from any state to any other state. This implies irreducibility. And if x equals y, this is still true, and so that means that at the next time step you can still be in the same state. This means that this state must have period 1. Remember that the period of a state is the GCD, greatest common divisor, of the set of n, such that Pnxx is strictly positive. In this case, P1xx or Pxx is strictly positive. So this implies that all states have period 1. Alright, so we have the correct ingredient. From the assumption here, we can deduce that the epsilon skeleton not only is irreducible, it's also aperiodic. So we must have this conclusion. If the epsilon skeleton share the same property as the continuous time Markov chain in terms of transience, null recurrence, and positive recurrence. So to prove this, notice first that, so this is what we want to prove. Processes xt and epsilon skeleton have the same positive recurrent, null recurrent transient states. And the first step is to observe that if you assume that xs is different from y, I'm looking at the continuous time process first. For all s in 0t, now remember that this time in continuous time corresponds to the time interval 0t over epsilon for the epsilon skeleton. If the continuous time Markov chain does not visit state y in this time interval, then the epsilon skeleton same is not going to visit that state in this over time interval 0t over epsilon. Alright, so this means that if the number of visits in state y for the continuous time Markov chain is finite, then the same is true for the epsilon skeleton. Or if the mean recurrence time, expected amount of time you need to go from y to y for the continuous time Markov chain is infinite, the same is true for the epsilon skeleton. From that, you deduce that if xt is transient, then the epsilon skeleton must be transient. Or if xt is null recurrent, then the epsilon skeleton must be also null recurrent. Alright, so now the next thing we want to prove is the same implication but for positive recurrence. So now the idea is just to notice that if the continuous time Markov chain visits state y at some time t that is between n-1 epsilon and n epsilon, I'm taking two multiples of epsilon that corresponds to time n-1 and time n for the epsilon skeleton, then if at some time t xt is equal to y, then there is a positive probability, okay, uniformly bounded away from 0, that the epsilon skeleton also is going to visit state y, this time at time n epsilon in continuous time, and at time n from the point of view of discrete time. The proof is simple. The idea is just to see that if this process is in state y at time t, then at time n, the epsilon skeleton is still going to be in state y if the process xt did not have time to jump before time n epsilon, but clearly because t is sandwiched between those two multiples of epsilon, the difference between those two times is less than epsilon. And so the probability that this happens is going to be larger than the probability that this did not jump in the next epsilon unit of time, because the waiting time until the next jump is exponentially distributed with rate minus qyy. This probability must be larger than exponential epsilon qyy. For all epsilon positive, of course, this is strictly positive. So this implies that each time the continuous time Markov chain visits a state, there is a positive probability that at the next multiple of epsilon time, the epsilon skeleton also visits this state. And from that, we can deduce that if xt visits y infinitely often, then the same is true for the epsilon skeleton, but also that if the expected amount of time it takes for the continuous time Markov chain to return to state Y is finite, meaning the process is positive recurrent, then the same is true for the epsilon skeleton. From that, we deduce that if xt is positive recurrent, then the same must be true for the epsilon skeleton. So in conclusion, we have that if the continuous time Markov chain is irreducible and transient or null recurrent, then the same is true for the epsilon skeleton, but even better than that, we have eperiodicity, and so we can conclude this. At this stage, eperiodicity is not needed. That's more at this stage. At the opposite, if the continuous time Markov chain is irreducible and positive recurrent, then not only the epsilon skeleton is irreducible positive recurrent, it's also aperiodic, and so we have those conclusions here. So eventually, to conclude, the idea is just to say that we can use the result from discrete time Markov chains. Again, I proved this theorem from scratch in chapter 7 for discrete time Markov chain. So just by applying this result and using the fact that the continuous time Markov chain and the epsilon skeleton share those same properties, we can conclude that this result for discrete time Markov chain is again true for the epsilon skeleton, and so the process xt, because this process follows closely this process here, the continuous time Markov chain. So we are done with the theory, but to conclude this video, I'm going to use the result we just proved, the theorem we just proved, to show the existence of a continuous time Markov chain that is positive recurrent, but whose embedded Markov chain is null recurrent. So the idea, if you remember the theorem we just proved, is to use the fact that for an irreducible Markov chain in continuous time, but also in discrete time, the existence of a stationary distribution is equivalent to positive recurrence. And so the idea, to show the example I just mentioned, is to find a continuous time Markov chain that has a stationary distribution, but whose embedded Markov chain does not have any stationary distribution. So obviously, to make sure that the embedded Markov chain does not have a stationary distribution and is not positive recurrent, we need to assume that the state space is infinite. That's something I proved in chapter 7 already. So we need to start with an infinite state space. What we are going to take is the set of all the non-negative integers, 0, 1, 2, and so on. All right, so we are going to assume also that the continuous time Markov chain is defined like that. From any state or integer, you can jump to the previous or next integer with those rates here. The numbers indicate the rates. The only exception, obviously, is for 0. You cannot jump left because -1 is not in the state space. In general, if the process is in state x, it's going to jump to x plus 1 at right x and to x minus 1 at right x plus 1. The only exception, again, is for 0. From 0, you do not go to 1 at right 0, you go to 1 at right 1. But for all the other states, the rules are like that. Go to the right with right the state, go to the left at right the state plus 1. All right, so we need to prove that this process, this continuous time Markov chain, is positive recurrent. For that, we need to find a stationary distribution. Earlier in this video, we proved that reversible implies stationary. In this case, it turns out that the unique stationary distribution, of the process is reversible, so we can use reversibility to find it. Things are a little bit easier. It's easier than solving pi q equals 0. So in this case, the detailed balance equation reduced to those equations. So to check the existence of a reversible distribution, we need to prove the existence of pi such that in general, pi x qxy is equal to pi y qyx. But clearly, qxy is always equal to 0 when x and y are distance more than 1 apart. So it's enough to prove the result to check those equations when y equals x minus 1 or x plus 1. By symmetry, it turns out that just looking at y equals x plus 1 is enough. So the goal is to find a vector pi or a distribution pi such that pi x q x x plus 1 is equal to pi x plus 1 q x plus 1 x. So for that, I'm going to do the following. First, I'm going to rewrite to try to express pi x using pi x and pi x plus 1 in general, or pi z plus 1, and use the fact that the ratio of those two terms is known. It depends on the transition rates. So to use this ID, I'm just going to write pi x as pi 0 times the product from z equals 0 to x minus 1 of pi z plus 1 over pi z. So this equation is indeed correct. Notice that here you have what we call a telescoping product. If you expand this, you get exactly going backward pi x over pi x minus 1 times pi x minus 1 over pi x minus 2, and so on up to pi 1 over pi 0. Eventually, all the numerator and denominator cancel out, except the first numerator and the last denominator. This product is just equal to pi x over pi 0, but times pi 0, that indeed gives you pi x. Now, using this equation, but for x equals z, you see that pi z plus 1 over pi z must be equal to q z plus 1 over q z plus 1 z. That's the term we have here. Okay? Now, we know those rates explicitly. Look at the product of the numerator first. That's exactly the rate at which we jump from 0 to 1, times the rate at which we jump from 1 to 2, times the rate at which we jump from 2 to 3, and so on, and rate at which we jump from x minus 1 to x. That's exactly the product 1 times 2 times 3, and so on, up to x minus 1. That's equal to x minus 1 factorial. If you look at the product of the denominator, that's exactly product of the rate going backward here. That's going to be exactly 2 times 3 times 4 times 5 up to x plus 1. That's x plus 1 factorial. Eventually, you obtain that this is equal to pi 0, x minus 1 factorial over x plus 1 factorial. That simplifies into pi 0 over x plus 1. Now notice that the infinite sum for x equals 1 to infinity of those terms is finite, which means that the set of reversible measures, as opposed to distribution, the set of reversible measures all have a total mass finite. And so from this set of reversible measures, you can extract a reversible distribution that is a stationary distribution. That's how we conclude. Then eventually you see that if you take pi 0 between 0 and 1, this infinite sum of pi x here, using this expression, is of the form 1 plus infinite sum for x strictly positive of 1 over x plus 1 times pi 0. Notice that I start the sum at x equals 1 and I add a 1 here because pi 0 does not satisfy this equation. There is again an exception for 0, but you see that this sum here is finite, and so for all pi 0 between 0 and 1, this sum times pi 0 is again finite, so you can divide all the pi x by this sum, and from that you extract a reversible distribution, which is stationary distribution. And so by the previous theorem we proved, the existence of a stationary distribution is going to imply the fact that the process xt indeed is positive recurrent. So now, to conclude, we need to do the same work, but with the embedded Markov chain. So the first step is to write the transition probabilities of this process. This can be done easily by using the superposition property for Poisson processes or the exponential random variable. Notice that when you are in state 0, you have to go to state 1 at the next time step. So P bar 0, 1, that's the probability that the embedded Markov chain yn goes from state 0 to state 1 in one time step. That's equal to 1. That's deterministic. For the other transitions, all x strictly positive, you go to the next state at rate x, previous state at rate x plus 1. This means that the time you wait until the next jump is exponentially distributed with parameter 2x plus 1. And the probability that you jump to the right is exactly equal to the rate at which you jump to the right divided by the overall rate. So that's going to be x over 2x plus 1. Transition to the right, transition to the left is going to be x plus 1 divided by 2x plus 1. Here I'm using the superposition property to find those transition probabilities. You have them here. Jump to the left, jump to the right with those probabilities. So now, to prove that we do not have any stationary distribution, we cannot do the same trick as here and prove the lack of reversible distribution, because lack of reversible distribution does not imply lack of stationary distribution. Reversible implies stationary, but no reversible distribution does not imply no stationary distribution. So instead, we need to solve the full system P equals pi, where P is the transition matrix of this Markov chain. So the coefficients are here. And doing this, doing some calculation, I just skip the calculation, you can prove that the solution to pi bar, P pi bar is going to be, as opposed to pi, the potential stationary distribution, but for the process yn. So pi bar P equals pi bar gives you that pi bar x must be equal to pi bar 0 times 2x plus 1 over x plus 1. So you find again the x plus 1 here in the denominator, but now you multiply by 2x plus 1. Now the infinite sum of those terms here is equal to infinity. This shows that the set of stationary measures for the process all have sum of the coordinate equal to either 0 or infinity. You cannot rescale any of those measures to get a distribution, so we do not have any stationary distribution in this case. So more precisely, we have the following. If I assume that pi bar 0 is strictly positive but less than 1, then this infinite sum of the pi bar x here is going to be of this form. That's equal to infinity. It comes from the fact that when x is large, 2x plus 1 over x plus 1 is of the order of 2x over x squared, that's 2 over x. Infinite sum of 2 over x is infinite. So this is infinite, so there is no way to rescale any of those solutions to get a distribution. And so conclusion, the process yn does not have any stationary distribution. And by the theorem we just proved, that is also true in the case of discrete time Markov chain, and I proved that in chapter 7, we deduce that the process yn cannot be positive recurrent. But we explained earlier that yn and xt share the same recurrent state or transient state. This means that yn, because xt is positive recurrent, must be recurrent, but it cannot be positive recurrent. And so conclusion, yn is null recurrent. Alright, so in this case, for instance, what we can conclude is, for instance, that if you start the process at 0, because the two processes are recurrent, we are going to return to zero in a finite time, but this time of return to state zero is as a finite expected value for the continuous time Markov chain, but an infinite expected value for its embedded Markov chain.